My name is Shahriari, and this is a lecture in a series of lectures on undergraduate abstract algebra based on my book, Algebra in Action, a course in groups, rings, and fields. This particular lecture is about Lagrange's theorem. So I have a group G and H, a subgroup of G, and I have an element X in G. Then Hx denotes the set of elements of the form Hx, where H is in H. So you take every element of H and multiply it by X, and you get a set of elements, and that's called the right coset of H in a G. It depends on what X is and what H are, what this set will be. For example, if you take X to be identity, you get H back itself. If X is not identity, then you do not get a subgroup, you get a set of elements that's called the right coset of H in G. Index of H in G, which we write with an absolute value sign G colon H, and we read that the index of H in G is the number of right cosets of H in G. If that number is infinite, then we say the index is infinite. H equals H is one of the right cosets, and the right cosets partition G. When you look at the different elements and find all the possible right cosets, you will get a partition of the group. These are things that we discussed in the previous lecture. Now, why is that? That's because right cosets are orbits of an action of H on G by left multiplication. You can prove this directly, of course, and you don't need actions, but the way we approach this whole subject is that by looking at different actions of the group, we see all kinds of new properties. And we looked at the left multiplication of a subgroup on a group as an action, sometimes called the translation action, and the orbits of that action are exactly the right cosets. And orbits of any action partition the set. Here, the set is the group because the subgroup is acting on the set, which is the group. Moreover, we showed in the last lecture that all right cosets have the same cardinality as H. They are the same. If H happens to be finite, they're all finite, the same size as H, but in general, they have the same cardinality. There's a one-to-one onto map, a bijection between any two right cosets. These are all the things that we saw in the previous lecture. And from this, the Lagrange's theorem follows immediately that if you have a finite group and H is a subgroup of G, then the order of G is the same as the order of H times the index of the subgroup. In particular, the order of H divides G. And the proof of this is very straightforward. In fact, I already said it. H acts on G by left multiplication. The orbits of the action are right cosets, and the number of orbits is the index of H in G. That's by definition. Each of these orbits have the same size, and they partition G. So the order of G is going to be the number of the sets in the partition, the parts in the partition, times the size of each partition. H is the size of the parts, and the index of H in G is the number of parts. And so when you multiply them, you get the order of G. But the important thing here is the size of H divides the size of G. Let's look at consequences of this. So let's start with a finite group, and I'm not going to even tell you what I'm going to prove until I prove it, because Lagrange's theorem actually helps us prove things. You start using it and you'll end up proving things even without noticing. So let's say we have an element A in G, and what am I going to prove? Well, I don't know yet. So I start with that element in G. Lagrange's theorem is about subgroups, and in fact, in group theory, we like to look at substructures and structures as opposed to elements. So we like to translate things to subgroups so that be able to say something structurally about the group as opposed to think about single elements. So if A is an element of G, then we look at the subgroup generated by that. What is that? That's the smallest subgroup of G that contains A. It's the intersection of all subgroups that contain A. It's you go in the group, take A, and throw in everything you need to make a subgroup. So you need identity, for example, and you need all the powers of A, positive and negative powers of A. But Lagrange's theorem says that if this guy is a subgroup, its order must divide the order of the group. But the order of the subgroup generated by A, that has another name. That's called the order of A. Order of the element is the least positive integer, such that when you raise A to that power, you get identity. So what we just proved is that the order of A divides the order of the group. So now we know that the order of every element in the group cannot be independent of the size of the group. The order of any element divides the size of the group. And this is, if you think about it, a little bit odd. Because, for example, it says that if you have some kind of a geometric object and you find one of its symmetries, for example, this is just an example, and that symmetry happens to be order 5, meaning that symmetry, if you repeat it 5 times, you get the object back where you started. then the total number of symmetries of that object can't be 12, or it can't be 81, or it can't be 47. It has to be a multiple of 5. Somehow or another, one symmetry puts a restriction on the total number of symmetries of the object, or thought the other way around. If you know the total number of objects in the symmetry group of an object, then there is restrictions on what kinds of symmetries that the object can have, what the order of those elements are. And this is not 100% trivial. I mean, this is something that you would have to argue and think about to see why this is true. Another corollary, a consequence of what we just proved, is that if you start with a finite group and it has n elements, the order of G is n, like maybe there is 135 elements. If you take an element in the group and raise it to that power, you'll always get identity. If you're an element of a group, it's not like you can say, well, I want to be of order 24. It always will be the case that depending on where you live, the group you live in, that puts some constraints on you. And in particular, this says that whatever you are, when you multiply it by itself as many times as the size of the group, you always will have to get identity. Again, not a trivial fact, but a trivial consequence of Lagrange's theorem. So we just proved that order of A divides the size of the group, then n is some number times order of A. And then if you look at A to the n, the thing we want to show is identity. We are taking A to the power k times order of A, but that's A to the order of A raised to the power k. And A to the order of A, by definition of what the order is identity. And so we get identity. And so this fact also follows from Lagrange's theorem. We want to apply Lagrange's theorem and try to sort of understand some groups. So let's say that P is a prime number. G is a group of order P. So I'm sitting in my room and a group of order a prime number walks through the door. What can I say about that group? One is not a prime. So there is some element other than identity. Let's pick that. Let's pick one like that, arbitrary X. And again, let's look at the subgroup generated by that. And the subgroup generated by that is a subgroup. And so by Lagrange's theorem, its order divides the order of the group. But the order of the group is a prime number. So the size of this guy is either 1 or P. Can't be 1 because it already has identity and X in it. And so got to be P. That means that the size of the subgroup generated by X is P, but that P is the size of the group. That means that that element generates P. So we got two things. This arbitrary non-identity element generated the whole group. So that means that G is cyclic. So let me write down what we just proved, that if you have a group with of order prime number, and if you take a non-identity element, then that non-identity element is a generator. So all non-identity elements are generators, and the group is cyclic. So we now have all of a sudden characterized with hardly any effort all groups of prime order. Two cyclic groups of the same order are isomorphic. So in particular, this group is going to be isomorphic to Z mod PZ, which is our go-to cyclic group of order P. So this says that up to isomorphism, there's only one group of order 47. It's just Z mod 47Z. There is no other group of order 47. And we just got this by looking at Lagrange's theorem and applying it to a subgroup generated by one element. Actually, we know more about this group of order 47. Not only we know that it's cyclic if a group of 47 walks through my door, not only I know cyclic, but I also know that it has many generators. Everything other than identity is a generator. We could have proved all of these, that part very straightforwardly by itself. But now this is all a consequence of Lagrange's theorem. By the way, this is not true of groups of order 48 or 46. There's not just one of them. There are quite a few more of them. But 47, there's only one. Again, when you go up the ladder of asking, well, how many groups of order 2 there are? Well, 2 is a prime, just one. Order 3, just one. Order 4, there's 2 of them. There's Z mod 2Z cross Z mod 2C, the Klein 4 group, and the cyclic group of order 4. 5, there's only one group of order 5. 5 is prime. 6, there are 2 groups, S3 or D6, the same thing, or Z mod 6Z or Z mod 2Z cross Z mod 3Z, which is the same as Z mod 6Z. And you can go up when you get to groups of order 8, there are 5 of them. But then when you get to groups of order 11, there's again 1 of them. So it's sort of a weird sequence of how many groups of each order there are. Okay, let me show you how we might apply Lagrange's theorem to a slightly more complicated group. So let's say that I have a group of order 1081. So I'm again sitting in my room, and this time a group of order 1081 walks in. And 1081 is 23 times 47. Okay, so what? I'm going to look at the center of this group because I'm interested in finding out how do I know about elements of the group commuting. Commuting is not a part of the definition of a group, so two elements of the group do not have to commute, but sometimes they do, and I want to know more about that. If a group is abelian, then its center, then everything commutes. Now, the center of the group is the elements of G that commute with all the other elements. Identity is one such thing. Identity always commutes with everything, and so identity is in the center, but there may be other elements in the center or not. But what we know, so I want to know this group of 1081, what are the possibilities about the size of the center? But the center is a subgroup of G, we have proved that, and because of that, Lagrange's theorem applies. So this already tells me something. It tells me that the size of the center is either 123, 47, or 1081. So either just the identity commutes with everything, or 23 elements commute with everything, or 47 elements commute with everything, or everything commutes with everything if the group is abelian. This is already sort of pretty amazing. Like, why is that? Like, if you have 1081 elements forming a group, why does it have to be that you can't have 20 of them be the number of elements that commute with all the other elements? Got to be either 23, 47, 1081, or 1. That's it. Okay. But we can actually say a lot more than that using Lagrange's theorem. So let's see. So again, we have a group of order 1081, 23 times 47. We have already said that size of the center is either 123, 47, and 1081 by Lagrange's theorem. But can the order of the size of the center be 47? Is that a possibility? Well, let's see. If it is 47, then there's tons of elements outside of the center. Let's pick one of them. So let X be one element that's in the group, but not in the center. Now I want to know things about this guy, whether how many things it commutes with. In fact, what I really want to know is that, can it really be outside the center? Is it in the center or not? But in mathematics, we don't really like binary questions. Instead of questions whose answer is yes or no, we rather attach a structure to them and ask a question where the answer is a range of answers. So instead of asking, is X in the center or not, I'm going to ask, what's the size of the centralizer of X? What's the centralizer of an element? The centralizer of an element is all the elements that commute with that one element. And of course, if the centralizer is the whole group, then I know that X is in the center. And my assumption that X was in G mod center of G would then be incorrect, would be a contradiction. So what is the size of the centralizer? What are the centralizer, again, is all the elements of the group that commute with X. Identity is one of them, but let's see. Now, the centralizer is also a subgroup. We have proved that, but it's also because the centralizer is the stabilizer of an action. What action? The conjugation action. But let's not get distracted by that. Let's just know that this guy is a subgroup. And by Lagrange's theorem, the centralizer, just like the center before, because that was a subgroup, its order can only be 123, 47, 10, 1081. But do we know already anything in the centralizer? Yes, we do. We know that every element of the center is in there, because the element of the center commutes with everything, including X. And we had assumed that the size of the center was 47. So we already know 47 things in the centralizer. So the size of the centralizer cannot be 1 or 23. But we also know that X itself is in the centralizer. X commutes with X. And X was not in the center, supposedly. So that gives us at least 48 elements that are in the centralizer. If there are 48 elements, by the choices that Lagrange's theorem gives us, we have no choice but to conclude that the size of the centralizer must be 1081. But that means that X is in the center. But we'd assume that X is not in the center. That's how we started. That's a contradiction. And that proves that our original assumption that the center of G had 47 elements was incorrect. So the center of G cannot have 47 elements. So now we're down to 123 and 1081. And of course, it begs the question, can the size of the center be 23? The previous argument doesn't quite work, because if you take something outside of the center and then say that, okay, the elements of the center are in the centralizer and itself is in the centralizer, that gives us 24 elements. It's still possible for the centralizer of that element to have 47 elements. but we can tweak that argument a little bit. So assume that the size of the centralizer is 23. I mean, the size of the center of G is 23, and pick an element, again as before, not in the center. And again, ask, what's the centralizer? You see a pattern. This is the sort of the kind of thing we ask. What's the size of the centralizer of X in G? How many elements could possibly commute with X? But Lagrange's theorem, again, the size of the centralizer is either 1, 23, 47, and 1081. What elements do we know in it? Well, we know that every element of this center is in it. So that's 23 elements. And we know X is in it. So that means that we have 24 elements. So that means that the size of the centralizer could be 47, or it could be 1081. But could it be 47? If it is 47, then the centralizer of this element is a group of order 47. And inside it is the whole center of the group. And the center of group was supposedly had 23 elements. So the centralizer would then have a subgroup of order 23. But the centralizer supposedly have 47 elements. And a group of order 47 cannot have a subgroup of order 23 by Lagrange's theorem. Therefore, this is impossible, and therefore the size of the centralizer will have to be 1081. But that means that X is in the center again, and that's again a contradiction, and so the size of the center cannot be 23. So putting that all together, what did we prove? We proved that if you have a group of order 1081, then either G is abelian, meaning that the center is everything, or else the center is just the identity. And now, this argument doesn't say that we have those two cases. It just says that we have limited to those. And you might say that, well, maybe if you're more clever, we can do even better than that. We certainly know an abelian group of order 1081. We know a cyclic group of order 1081, which is abelian, Z mod 1081Z. So certainly it's possible for G to be abelian. To see whether or not it's possible for the center to be identity, you would need to construct an example, and that is possible in this case. But I'm not going to do that right now. We will do that in a much later lecture. Okay. Now, so those were some of the uses of Lagrange's theorem. And if you're, as we saw, if you're clever, you can go far. But using Lagrange's theorem, we want to focus a little bit on the indices, the indexes of subgroups. So if you have a finite group, and if you happen to have two subgroups, H a subgroup of K and K a subgroup of G, then this theorem says that the index of H in G is the product of the index of K in G and the index of H in K. Now, do those terms actually make sense? The index of H in G is the number of right cosets of H in G. The index of K in G is the number of right cosets of K in G, okay? And the index of H in K is the number of right cosets of H in K. And that makes sense because H is a subgroup of K, and therefore we can find its right cosets. Okay, the way we think of this is that, well, here's a part of the Hasse diagram of subgroups of G. So all that means is that H is a subgroup of K is a subgroup of G, and we drew that little diagram with H at the bottom, and there's a line going from H to K, denoting to us that H is inside K and then K is inside G. The way we want to think of these indices is that I think of G mod K, the index of K in G, as the index of K in G, as that top part, as the part of the length of the line between K and G, the edge between K and G. And likewise, the index of H in K is the length between H and K. And the length between H and G is the index of H and G. Now, the only thing about these lengths is that they're multiplicative. They're not additive. You don't add them to, like if you put two of these together, you don't add the lengths to get the length of the bigger one. You have to multiply them. If you really want to add, then you would have to take the log of these. But so that's the way we think. We think that if you take this index and that index and multiply them, you get the bigger index. That's the way to think of it. The proof of this actually is pretty straightforward as long as G is a finite group. Because if G is a finite group, then by Lagrange's theorem, the index of H in G is the size of G divided by the size of H. And again, by Lagrange's theorem, the index of k in G is the size of G divided by size of k. And the index of H in K is the size of K divided by size of H. All of those are Lagrange's theorem, because Lagrange's theorem says that if you can partition your group, your finite group, by the cosets, each of them has size H, and there is the index number of those. And so all of these follows. Now, if you multiply the last two of these things together, these two fractions together, you get the first one, because the size of K's cancel. That's all it is, multiplying two fractions and getting the result. This result is actually true even if G is infinite, as long as the index of H in G is finite. But then this proof will not quite work, because then we can't talk about the size of G, and you need a better proof. You need a one-to-one map that shows you that you can do this. Okay, now one particular case of this is if I only look at one subgroup H, because in that case, I can also talk about indices. So the index of H in G, well, that's that. But I can also talk about the index of E, the identity subgroup in H, and that's just the size of H, because the number of right cosets of identity in H is the same as the size of H. And so then that says that if you take H and multiply it by the index of H in G, you will get the index of identity in G, which is the size of G. And that's actually Lagrange's theorem. So Lagrange's theorem is that the size of G is the size of H times the index of H in G, and that's a particular case of this. So you can think of this, if you like, as a generalization of Lagrange's theorem. Okay, so now why did I say that? Here's one example of how I can use that. I'm going to say that if G is a finite group, and if you look at the center and you look at the index of the center, again, the way I'm thinking of it in my head is that's the top part of the diagram between center and G, but this is the number of right cosets of the center of G and G. That cannot be a prime number. And in fact, if you go back to the proof that I did for the group of order 1081, you can streamline that if you knew this proposition. Okay, and I'm going to give you a proof by diagram. I'm not going to write down a lot of things. I'm going to tell you how a group theorist would be thinking of this. So the way a group theorist would be thinking of it, they would draw this diagram and they would say, okay, we have the identity subgroup, then we have the center, and then we have the group. Okay, and then you would say, and then what we know is that index is a prime number P. All right, then what? Then I'm going to do the thing we've always been doing, pick an element of G that's not in the center, okay? And then ask, where is the centralizer of that element? Instead of asking what's the size of the centralizer, I'm going to ask, where is the centralizer? Well, the centralizer contains the center, because the center of the group are the elements that commute with everything, and certainly those elements commute with X. And therefore, the center is a subgroup of the centralizer, and the centralizer is subgroup of the group. And so the centralizer is somewhere on that line between the center and the group. And now we are back to the previous theorem that we had. So this says that now if I look at the index of the centralizer in G, and if I look at the index of the center in the centralizer, those two have their product has to be the index of the center in G, which is that prime number. But prime numbers don't factor. So I can't have this factorization. There is nothing between the center and G. The center is what we call a maximal subgroup. If the index is a prime number, then that subgroup had got to be a maximal subgroup. There can't be anything in between, because if there was, then that prime number would have to get factored as G mod as the index of the centralizer in G, and then times the index of the center in the centralizer. Those are sort of mouthfuls. So, but the centralizer is somewhere. Why can't it? Where is it? Well, if it's not in the middle there, then it's either at one of the two ends. Well, it can't be at the center, because X is already in it. So the centralizer is clearly bigger than the center. So it must be all the way at the top. So the centralizer must be G. And that means that X must be in the center. But we had picked X not to be in the center. You see déjà vu. This is the same argument as before, but this time we're just doing it with a diagram. And that's a contradiction. And if we have a contradiction, then that means that our original assumption that the index was a prime was incorrect. So we started with assuming that the index is prime, and we got to a contradiction. And that brings me to the end of this lecture on Lagrange's theorem. On the next lecture, we will look at some applications of Lagrange's theorem to number theory. Till next time.